Okay. All right, everyone. So can you guys see my screen?
Yeah.
Okay, that's good.
Yeah.
All right, so let's start now. So we only have 2 lectures left. And today we are going to finish the effects of turbulence on the convection. And next class, we will talking a little bit for the two-phase convection, like boiling and condensation. So then we will finish our whole semester and ready for the exam. In the last lecture, we're starting to introducing some basic concepts for the turbulence. We're talking about that, turbulence basically is including all the fluid quantities, including a fluctuating parts, comparing to the mean part. And the way we have several ways to do the averaging. And in this class, we only focusing on the Reynolds averaging. So basically, in this class, we were talking about that the effects of the turbulence on both forced convection and natural convection. We're focusing on 2 questions here. The first thing is that in which condition the flow will become turbulence, right? Because we need a criteria to know that is this a laminar flow or turbulent flow. The second question is that if the flow become turbulence, all those hydraulic and thermal correlations that we derived before, like those friction factor, and those Nusselt number we developed for those laminar external flow, like the laminar flow over the flat plate, and the laminar internal flow, like those laminar fully developed laminar flow inside the circular pipes. Those correlations will become invalid, and we will have the new, correlations to use. So this is basically the 2 questions we are going to, to solve in this lecture. Today's lecture will majorly including the 2 parts, 2 chapters. The first one is we are talking about the external turbulent flow, the turbulence flow for the, especially for the, we are talking about the turbulent flow over a flat plate. Before, in previous, in chapter 2, we studied the laminar boundary layer theory to study the laminar flow. And in this case, if the flow becomes turbulence, right, we will basically the boundary layer will also become the turbulence. So we were talking about that, the characteristic of the turbulent boundary layer problem. And the second part of the lecture, we are talking about the internal turbulent flows. Basically, is corresponding to our chapter 3's content, where each in chapter 3 we're talking about the laminar flow inside of pipes, and in this case, we will talk about the the turbulence flows in circular pipes. Okay, so let's starting from the first one. First one, we are looking for the turbulent flow over a flat plate. Here I draw a sketch that if a flow over a flat plate, parallel flow over a flat plate, what the flow regimes will look like if the flow is keep developing along the plate direction, if this plate is long enough, okay? And in the beginning, the flow, the boundary layer will be developing starting from the tips of the plate. At that stage, okay, if we calculate the local Reynolds number, the local Reynolds number is, it's proportional to the x coordinate, right? It's rho u infinity x divided by mu, and with that x coordinate become increasing, and the Reynolds number basically will increasing. We know we know that the Reynolds number basically is a ratio between the initial forces or the viscous forces, right? And if the Reynolds number keep increasing, that means that the viscous force will become smaller and smaller, and the initial force becoming keep increasing. At some point, okay, because viscous force is like to try to keep the flow, organized, because that they keep to drag the adjacent fluid particles, to have the same behavior as the current fluid particle. Okay, when the viscous effects become comparing with the initial forces, become smaller, and at some point, okay, the turbulence can happen. So that the turbulence happen means that the flow field become chaotic. Okay, it become disorganized. You see the vortices, and the fluid properties will have fluctuating quantities, which is statistically following some statistical rules. Okay. So basically, if this plate length is long enough, we can distinguish that the flow region into 3 parts. The first part is the laminar flow, and the part between the laminar flow and the turbulent flow is the we call the transitional region. The transitional region is that at that stage, okay, the turbulence effect has already begun to to show, but it's still not dominant in the flow field. So it's like you see a little bit changing of the fluid stream length, direction of stream length. And after some Reynolds number, when Reynolds number keep increasing, and the whole flow field becoming fully turbulent. So basically, we will have a critical Reynolds number. Okay, this is a critical Reynolds number. Like we can think that if the Reynolds number is smaller than this critical Reynolds number, the flow becomes laminar. Okay, so usually speaking, okay, different literature, okay, using the different value of the critical Reynolds number in these cases. Usually speaking, the Reynolds number critical is some value between 3.5 times 10 to 5 to 5 times 10 to 5. Okay, and in this picture, we write 5 times Reynolds critical Reynolds number equal to 5 to the 5 times 10 to the power 5. This is the most commonly, critical Reynolds number we use. Okay, and also you can define another Reynolds number. Here I denoted as Reynolds number T. You can think that if the flow, if Reynolds number is larger than this Reynolds number T, okay, it can be fully turbulent. And usually speaking, this Reynolds number T value is some value between 9 times 10 to power 5 to the 1.3 times 10 to 6, some value between them. Okay. Another way you can calculate, this Reynolds T is that there's a relationship between this location of this X critical value and X T value. X critical value is basically you compute from this critical Reynolds number, okay? And the X T value basically you calculate based on from this full turbulent Reynolds number. From the experimental data, okay, people basically saying that XT over XCR equal to approximately equal to 1.39. Okay. So what does it mean? That means is that if you choose a critical number, critical Reynolds number like 5 times 10 to the power 5, you can then using this correlation, okay, XT over XCR equal to 1.39. You can also compute this fully developed Reynolds number, this bound R equal to the T. So this is the condition where you can determine that if there is this flow or flat plate, are they laminar or turbulent? Okay. So this is where when you're using that, if you want to consider transitional flow region. In many cases, okay, in many cases that this transitional region, okay, is also considered as some turbulent field. What I'm saying is that in some study, okay, they didn't consider the transitional effects. They only consider that either flow is only two flow regimes. Either the flow will be laminar or they will be turbulent. In that cases, you can just using the critical value on this RECR equal to 510 to times 10 to power 5. And you can see that if that is the case, you can just see if Reynolds number is smaller than RECR. Okay, you can see that the boundary layer is laminar. Okay, or you can see that if Reynolds number is larger than RECR, you can see that the boundary layer is turbulent. Okay, so this is answer our first question, that by what condition this flow or flat plate will be laminar or turbulent. Okay, and so let's take a look over the second picture here. Basically we show the detailed velocity profile in the laminar boundary layer and in the turbulent boundary layer. So in the laminar boundary layer, you can see that the profile is, in this boundary thickness profile, will eventually go to velocity will reduce to 0. Okay, so if you draw draw a slope, okay, regarding to the u velocity on the y direction, this slope here, you can see that this slope times mu basically will be this will be the tau w. It will be the wall shear force. Okay, so it will be equal to mu partial u partial y back to 0. Okay, and in the turbulent boundary layer, okay, the velocity profile actually will looks a little bit different than the velocity profile in the laminar boundary layer. You can feel like let me write it here. The velocity profile in turbulent boundary layer is much full. Okay, you can see that this is more full than this here, than the profile in laminar case, laminar boundary layer. Okay, what does this mean? This means that if you also draw a slope, okay, the velocity slope at the wall direction, okay, you will see that in the turbulent field, okay, this slope, okay, will be a little bit smaller than the slope here. The slope in the what I'm drawing here. du dy. Okay, so this slope will be smaller than this slope actually is larger, okay, because we are calculating du dy and it should be using this horizontal divided by this vertical space, okay. So this slope on the turbulence du dy actually will be larger than the slope in for the laminar cases. Okay, so what does this mean? This means that the tau w in the turbulent actually will be larger than tau w in the laminar. And this including, basically this is telling us that the turbulent in the turbulence cases, we will have larger wall friction. Okay, so this is the first thing we can observe from the velocity profile. And similarly, we can do the observe the temperature profile. Okay, so here we have that the temperature profile on the laminar case flow and temperature profile on the turbulent flow. It's same thing, okay? You can feel like, you know, on the turbulent field, actually, this, you know, the profile is also very full here. And let me see, dt, dy. Okay, I don't think this is drawn correctly here, okay? So it should be more slope at the end, something like this, okay? So make the slope a little bit smaller, not larger, okay? So this is a typo here. But basically, is I want to say is that the turbulence, okay? Similarly, okay? We will also that this Q wall for the turbulence will be larger than the Q wall of the laminar if the TW equal to constant, okay? For the constant wall temperature cases, the turbulence, the existing of the turbulence will also, you know, try to bring more heat from the wall to the flow, okay? So we have an issue here. So this is just some, you know, generally speaking, that what the effect of the turbulence for this problem. To solve the problem, we need to, you know the governing equation, right? How to solve, right? So this will be the, you know, what we got from our chapter 2, okay? The governing equation in the laminar boundary layer, okay? This is continuity, X momentum, and energy equation. The y momentum is neglected because that it will only giving you to show that the pressure is only a function of x, not a function of y. Okay. In the turbulent field, okay, the approximation we made in this laminar boundary equation in chapter 2 is still working. Okay, so you can think that this equation is still works for instantaneous quantities. Okay. So basically, you can see that this is still the governing equation for the instantaneous value of U, instantaneous value of V, instantaneous value of pressure, and instantaneous value of temperature. Okay. To obtain the Reynolds average the governing equation, then you just need to, you know, write this instantaneous value into two parts, right? Become U. This U will become U mean plus U prime. V will become to V mean plus V prime. Temperature will become temperature mean plus temperature prime. Okay, so what you need to do is that for this, you know, continuity equation, you just you do averaging directly, so you know that you get this average, Reynolds average the continuity equation. And for the momentum, you just do a little bit, you know, derivation. You know, first you rewrite the momentum equation, you put this U value inside this convection term, and then do averaging on the left and on the right. So remember one thing you remember is that, you know, when you do this averaging, this U bar square will not equal to this U bar square, okay? Or you have this UV, you cannot just write it as U times V. This is not working, okay? The reason is very simple, because that this bar, this averaging is if you're using time, right? This is T of 0 to T, something dt, right? So this is a linear operator, okay? This averaging, so it's linear. And this, if this term is nonlinear, so U times U times is nonlinear, so you cannot just, you know, using those distributive laws, okay, between their components inside, okay? You cannot do that on these nonlinear terms, all right? So you have this U squares on bar, and okay. I think I neglect one term here in the middle. Okay. This term. Okay. This equation is not coming from here. This equation is by you know, this equation is by you using this equation And yeah, you can do that. Okay. So this is from this equation to this equation. Okay. Basically, you rewrite this u here equal to u plus u bar plus okay. So basically, this u square, you can write this as u bar plus u prime. Okay, and do square. Okay. So it will be give you like a u bar square and plus 2u bar u prime, right? And plus u prime square to this bar, okay? And when you do 2 average on this thing, the same thing, okay? So this is still u bar square. And this will be 2u bar because this is constant. Is already the mean value, and then you do a u prime bar. And this will go to 0, okay? So this term is gone, and you have this u prime square, okay? So that's the reason that after you write from this equation to this equation here, you will have additional equation, additional term here. Similar things for the UV, you will have additional term U prime V prime here. So this is additional Reynolds stress we got, right? Based on our last class lectures, introducing. And you rewrite it again. Okay, you can put this U average out. So this will be the final X momentum Reynolds average equation. So comparing with this instantaneous correlation, so you will have 2 additional Reynolds stress term, partial X over U prime square bar and partial Y U prime V prime bar. Okay. And also for the energy equation, okay, when you do the Reynolds average, okay, you will also obtain 2 additional terms, partial U prime T prime on X and partial V prime T prime on Y. Okay. Also, we can do by scaling. Okay, we can also do some scaling analysis. So usually speaking, that the velocity fluctuating components, okay, fluctuating components on X and Y direction, they are the same order. U prime and V prime, we consider they are the same order because we consider they are the same velocity the fluctuation from the same ID, okay, from same size of ID. Either it's large or small ID. They are from the same ID, so we consider it's the same. Their order should be same. Okay. So if you compare this partial X U prime square average, so it will be order of U prime square of L over L. And if you do comparing this term, partial Y U prime V prime, and consider Y on the Y direction, the length scale will be coming to the boundary layer thickness delta, right? So this will be order of U prime. There's a square here, sorry. U prime square over delta. And remember that our basic boundary layer assumption we made in the chapter 2 is that we assume that the boundary layer is very thin, which means that this delta will be much larger, much smaller than this plate length L. Okay, delta smaller L. This is the fundamental assumption we made in the laminar boundary theory. So if you compare these 2 terms, we can see that this partial Y U prime V prime will be much larger than this partial X U prime square. So basically means that this term can approximate to 0. Okay, compare the other term, compare this term. And similar things, okay, you can compare this term and this term. And you can see that this term is also close to 0. Sorry, not this one. You compare this term and this term, you can see that this term is also going to 0. Okay. This is going to 0, okay? So if you write the final turbulent boundary layer equation here, you have continuity here. So this will be continuity, Reynolds average continuity. X momentum will be this one, but remove this component because from scaling, we know that this can be neglected. So this will be the final Reynolds average X momentum equation. And again, okay, the last one, the energy equation. So this term can go, and this will be the final Reynolds average the temperature equation in the turbulence boundary layer. Okay, so basically all these 3 will be so-called Reynolds average the turbulent boundary layer equation. All right. So we have this additional Reynolds stress term, right? We have two Reynolds stress term, additional one. One is in the this x momentum, and one is in the energy equation. We can using our you know mixed layer theory we have in the last class. So basically, we can you know rewrite this these two terms. Okay, you know we can define ID viscosity. You know, makes this minus rho u prime v prime equal to rho mu t times part u part y. This mu t, this nu t can be considered the ID viscosity, right? So you can rewrite this governing equation, momentum equation in this way. So absorb this term 2 into additional nu t here. Okay. And similarly, okay, for the energy equation, you can redefine this, you know, this Reynolds stress term to as additional ID thermal ID diffusivity alpha t. Okay, so that you can rewrite this Reynolds stress term into this one here. Okay. In the last lecture, I forgot to talk about the sign of this Reynolds stress term. Okay. You need to know that all this you know this additional Reynolds stress term basically is a correlation between this V prime U prime, you know, this fluctuating 18 quantities. This quantity is usually negative. Okay, we always consider is negative value. That's this is means statistically correlation between U prime and V prime. Well, why? There is a way to prove it to prove this. Okay, from mathematically. But another easy way you can think about this is that you know this U prime is velocity fluctuating on the x direction, right? And the V prime is fluctuating on the y direction. So think about this: if your U prime is increasing, okay, on x direction, so means that which means that your instantaneous velocity on the x direction will also increasing, right? So basically, it means that your U prime increasing, you're tending that U will be increasing, right? Okay. And what does that mean? That means that if you look in this, mass conservation or momentum conservation, okay, or if you're looking at the kinetic energy, right? So it's like if you increasing, okay, from if you still want to let the mass still conserve, basically you will you're likely to reduce the wave velocity. Otherwise because that you want to keep the mass flow rate same, right? The mass still conserved. And when V is decreasing, actually you're tending to reduce the V prime, okay? Or you can think the other way, okay? If U prime is increasing and V prime is also increasing, then you're tending to increasing both U and V. So you won't satisfy your mass conservation. So that's why is that if U prime, that's why is that this correlation is always negative, because that when you increase U prime, you tentatively reduce V prime, and otherwise you want to increasing V prime statistically, okay, increasing V prime, you're tending to reduce U prime, okay. So that's why this term correlation is always considered negative, and if this term is considered negative, you have this minus sign here, right? So this the whole term with this minus sign is will going to positive. The term will be tending to be a positive term. And also we know that this is the mean viscosity, momentum diffusivity term, right, due to the viscosity factor. So this is positive, and this is also positive. So that's the reason that we can consider that because this is positive and this is positive. That's the reason that we can consider that this additional Reynolds stress term with this minus sign is some additional, viscosity diffusivity on the momentum due to the turbulence. Diffusivity on the momentum due to the turbulence. Okay, so that's why we consider that it is rho nu t. Okay, similar. So we can including this mu plus nu t here. Like this will be some additional, momentum diffusivity due to the turbulence. Okay, if this sign U prime V prime bar is become positive, then you won't able to do that, because that in these cases this will not be a additional diffusivity term, will become a destruction term. Okay. This is the one way. Okay. Another way you can consider this U prime V prime is always negative is that because that if you take your turbulence class later on, you will know that you know I also talked about this in the last class, right? Because that there is a direction of the energy cascade in the turbulence, right? Because turbulence basically what we are seeing is that the kinetic energy basically is transferred from the large ID to small ID, and to smaller ID, and at the end, to the minimum scale of length scale, which is the Kolmogorov scale. At that point, then all the kinetic energy will be dissipated to the thermal energy. All right. So that means that we have a direction. Okay, we have a one-way direction from the large ID to small ID. So the reason why this term is always negative is because that this direction, okay, negative direction represents from the large ID to smaller IDs. Okay, that's why it's that we always think that this term is always negative. All right. Similar things. In the alpha t, okay, this term we can always also thinking that this is this v prime t prime is also always a negative value. So this can be an additional thermal diffusivity. So that's why we define this alpha t here, and the equation will be written in this way. Okay. In the end, okay, the governing equation, the Reynolds average, the governing equation in the turbulence boundary layer will become to this one, continuity equation, momentum equation, x momentum equation, and time energy equation. So we have the unknown we have here is we do not know u, we do not know the v. Okay, if this pressure here is usually equal to the free stream pressure. Okay, usually we consider this dp of dx. Okay, equal to dp infinity of dx. Okay, so that means that we consider that we know the pressure gradient already, and we do not know the temperature, and we do not know the mu t and alpha t. Okay, so we have these 5 unknowns, but we have 3 equations. That's why is that we need additional turbulence modeling. Okay, we need additional turbulence models like you can give you the mu t. Okay, either it from this one equation mixing layer model, or from those 2 equations k epsilon model or k omega model, whatever. But in the end, it will give you this mu t. And after you have this mu t, usually people doing is that we can calculate alpha t directly from a so-called turbulent Prandtl number. And this Prandtl number in our turbulence modeling, we usually just set it as some constant, okay, like a Prandtl, like this Prandtl number t equal to 0.7, like that, something like that. Okay, so this is the way we can solve this equation numerically. If you're interested and want to do this, you can even write your own CFD code to do this. Okay. All right. So, but in this class we won't talking about too much about that how we can solve this equation numerically. Okay. We try to find some analytical way or empirical way that how the the hydraulic and thermal behavior in the turbulence boundary layer. Remember that in the last class we talked about the velocity distribution close to the wall, right? So basically, this one is what we write in at the end of the last class. When you basically call the one common velocity profile in the region very close to the wall. Okay, there are other correlation given based on the different semi-spherical theory, okay, semi-analytical theory, or from just pure experimental data. Okay, so basically I want to letting you know that there will be many correlations to give you that what the velocity profile would looks like in the region very close to the wall. Okay, why this is important? Because that with this velocity profile, okay, so let's recall some what this u plus y plus means. Okay, so basically you remember that first we define a frictional velocity u star, which is equal to tau w divided by rho. Okay, tau w is the wall shear force, and then we define this u plus, it will be equal to u bar over u star, right? This is basically a non-dimensional value, and we define this y plus equal to y times u star divided by nu, okay? Kinetic viscosity. Okay, this is how we define y u star. Okay, so if we know, the importance of this study is that if we know the velocity, if we know the velocity distribution, okay, this you see here, we can try to find what this tau w will be, right? Because this tau w is directly related to the velocity distribution, right? We know that tau w equal to mu partial u partial y equal to 0, right? Equal to 0. So the important thing is that if we know this distribution, okay, if we choose one of them, we should be able to find what the tau w will be for this turbulent boundary layer cases. All right. So assume that we have a velocity profile u plus equal to fu equal fu means a function, okay, u function, velocity function profile of y plus. So this fu can be either of them, okay, any of them, okay. And assume we have a boundary layer thickness, okay, delta. We can see that at y equal to delta, u will become u infinity, right? Okay. So this u, remember that the definition of this u plus here and y plus here. So we just redefine that this will be u plus, okay. This will be u plus at the y equal to delta, okay. So this point, this value is just the u plus, okay, at y equal to delta, right? Because at y equal to delta, u will become u infinity and then non-dimensionalized by this tau w over rho by 1 over 2. This is the friction u star frictional velocity, okay. And similar thing, so this quantity here, this is the y plus, okay, at y equal to delta. And y plus is defined as y times u star divided by nu, okay? So basically you have this y times this u star divided by this nu here, okay? So this will be, so if you choose this point, if you select one point as a boundary layer, one point as a located as a boundary layer, so you can just put this value into this equation here, okay? So you looking this one, looking at this equation, okay? We do not know tau w, okay? This is what we want to know. And also we do not know the delta. So we have two unknowns, right, for this equation. So only the velocity distribution itself won't be able to solve this two value for us, okay? Two unknowns, okay? We need one more equation. One way to do this is that, you can consider a momentum integral equation, okay? Remember that the momentum integral equation can be related to the tau w over rho. If you can get this equation in our chapter 2's notes, lecture note. And also assume that there is no pressure gradient, okay, to make the thing simple, okay. And so this will be, you have this momentum integral equation. So this will provide you an additional, correlation. If you have this profile, you profile from this fu here, and you have tau w, okay. So this will bring you the second equation, okay. With this equation 1, equation 2, okay, they are sufficient to find both tau wx and delta x. Okay, you can find both the pressures. Sorry, you can find the both shear force tau w and boundary layer thickness delta. Okay, so solution, but solution, okay, will depend on which expression of fu you choose. Okay. The most simple, cases of fu is the so-called Prandtl's 1/7 power law. So the Prandtl's 1/7 power law basically means that fu equal to 8.7 y plus 1 over 7. Okay, this is the most commonly used, velocity distribution in velocity profile in a boundary layer. Okay, in the region near the wall actually. So this is very common one to use shown in the many textbook. And if you bring this fu value into this equation here and this equation here, this 1 and 2 equation here, you should be able to solve the tau w and delta. Okay, and the solution will including many complicated math operations, but we can try to do this in another way. Okay, basically this will be the result. Okay, if you're using the profile, this basically will be the overall result of the velocity distribution. basically it means that if you choose this one, it assume that this will be solution actually. But we can starting from this solution, we can just assume that we know this solution already, okay? So that we can try to derive other quantities. So basically means that in the turbulent boundary layer, the mean velocity over the free stream velocity will equal to y divided by delta to the power of 1/7. So that is why it's so-called 1/7 power law. Basically means that the velocity distribution inside this u infinity of y over delta will be 1/7 cases, okay? And if you know this velocity distribution here, and first, okay, first you can calculate what the boundary layer thickness delta, okay, and the boundary layer delta thickness delta can be computed, you can just assume that this is delta u, okay, equal to is where, u velocity, mean velocity, at the delta of u equal to 0.99 u infinity, right? So you can just try to using this equation to solve to not this one, okay, I make a mistake here. Let me remove this is not true, okay. So basically you have this velocity here, profile here, and you bring it to this equation here, and using this correlation shape by fu equal to 8.7 y plus 1/7 because they are the same thing, and you can get the turbulence boundary layer thickness, okay, delta over x will be equal to 0.373 Reynolds number minus 1/5, okay. And also you can calculate this both delta star and theta star, okay. Delta star is the displacement thickness, right? If you remember, this is 1 of u of u infinity, okay, dy, okay. This is the displacement thickness, and theta is the momentum thickness, right? Theta is 0 to infinity u of u infinity 1 minus u of u infinity of dy, okay. So you can just prove, bring this based on this definition here. You can define, you can prove that delta star is basically will be just 8 times and 72 of this boundary layer thickness, okay. So the final result will be that so if you using the so this is the definition of the friction coefficient for external flow, right? We define this as tau w over 1.5 rho u square, right? So this is what we define. So that's the reason that this tau w divided by rho u infinity square will be 1/2 of friction coefficient, okay? And this friction coefficient, okay, will be just equal to let me see how we can get this. So we just still solving from this equation, okay, because rho we have this tau w divided by rho u infinity square. So we have this tau w divided by rho. So you bring these two equations, okay, and the final solution will be this one. You do not need to know practice that how this is calculated, but you need to know that this will be the result. So this will be the local friction coefficient for the turbulent boundary layer. This is the mean, okay? If you do a mean calculation between 0 to x, what's the friction coefficient in the boundary layer? So this is the result, okay? This is the result, this result, and this result. Okay. If you want for this one, okay, if you really want to know that how this is got, it's basically calculated from this momentum equation, okay? Because that if you're looking that our momentum integral equation we derived in the equation 2, okay, in the chapter 2. you can relate this tau w to some, we have an equation called CFX over 2 equal to d theta dx, okay? This, you can find this equation in our chapter 2, okay? So basically means that after we know that this delta equal to 72 over 7 theta, so you can calculate theta, and you bring this theta to this equation, okay? You will get the CFX, okay? It's very straightforward. So, and then after you get this local value, you can integrate on x, okay, through 0 to x on x or 0 to L on L. You can get the average value for the pressure, wall friction, okay? So important things. So if you write these 3 things, okay? So let me write something to compare, okay? So if in the laminar cases, and if in the turbulent cases, for delta, for turbulence one, we have this delta over x equal to 0.373 Reynolds number x to minus y over 1, right? So this is the Reynolds number. This is the boundary layer thickness for in the turbulence field. And in the laminar result, if you recall our previous Bloch-Schulz solution, okay, the exact solution for the laminar boundary layer. So this delta over x for laminar cases will be equal to 4.92 Reynolds number x minus 1 over 2, okay? So now you see the difference, right? So 1 is delta x to the Reynolds power minus 1 over 2, and this is the delta over x to the Reynolds number minus 1 over 5. Okay, so if you times x to the right, so basically telling you that for the delta value for the laminar, okay, they are proportional to the x of 1/2, right? For laminar, if you times this x to the right hand side, and also remember that there's another x component inside this Reynolds number. So they will have, and for the delta of turbulent, so you will, what do you get? You basically get x equal to 4 over 5. So that's why is that when you draw this boundary layer thickness on this flat plate, right? So we see the laminar, and then we draw turbulent. That's why that this turbulence that has another, slope increasing as this transition point is going up, right? Because that this will become, for the turbulent field, this boundary layer thickness is proportional to the x to the power of 4 over 5. Okay, this is the first thing. You can also compare with CFX, right? And CFX for the turbulent field, what we have here is that you times this 2 on this side, so you will have CFX will be equal to, so what will be 295, right? 0.0259 times Reynolds number x of minus 1 over 5. Okay, so just times the 2 on this side. And for the laminar cases, okay, from our Bloch's solution, we have 0.664 Reynolds number x 1 over 2, minus 1 over 2. Okay, so this is another thing. So the mean value, is very simple, okay, because it's just equal to 2 of the local value, okay, for the both cases. So no, I'm making a mistake. It's not for both cases. It's only for the laminar flow you have this one. So for this CFX, for the mean value will be equal to twice of the 1.328. Okay, Reynolds number x minus 1 over 2. And this one, the mean value between 0 to x will be equal to this value, 0.037, 0.037 times 2. So this will be, this will be times 2 will be 0.074 Reynolds number minus 1 over 5. Okay, this will be the friction factor for the turbulent one. Okay, And so if you time after you calculate this, after you calculate the friction factor, you times the this velocity, 1/2 rho u squared, you can get the tau w. I think I make a big mistake in the beginning of the class. Okay? In the beginning of the class, I falsely saying that in the turbulent field, turbulence will be larger than this one. This is not true. It should be smaller. This is my fault. Sorry. The reason is that you can see that this slope is higher. This slope is smaller. Okay, du dy. I make the mistake. This is smaller slope. This should be smaller. You can also see it from here. So because this quantity is much smaller than this quantity, okay, and this value is much smaller than this value. So basically, turbulence will reduce the drag rather than increasing the drag. Okay, this is my fault. This is obvious because as I told you, because that turbulence is when the viscous force is comparatively smaller than the initial force. Okay, so because viscous force becomes smaller. Okay. All right, so I make a mistake here. And remember that this correlation you got here, this three equation you got here is based on this Planck's 1/7 power law. Okay, so this law is simple, so that we can easily derive this correlations for the boundary layer and friction factor on the turbulence boundary layer, but it's not accurate, very accurate. Because to get very accurate, you have some empirical correlations. Okay, this is one example that based on the experimental data, what the friction factor on a flat plate will be. Okay, this one should be more accurate than this one. This one, the reason we're introducing it is because it's simple, and this 1/7 power law of Prandtl number for this velocity distribution is used a lot in many turbulence study. Okay, for the flow near to the wall. All right, so and let's now emphasize this again. Okay, so a big mistake here. The turbulence is likely to reduce the viscous force here. Okay, rather than increasing. Okay. Let me think about this a bit. Okay, CFX. No. I made a mistake. No, this is not correct. This is still larger than, okay, turbulence TU dy. Turbulence the viscous force. So this will be the du here, and this will be the dy, right? So du divided by dy is this angle here. It's du beta dy. So this is still larger than this. Yeah, I'm sorry, I'm a big mistake. Another big mistake. We cannot compare this two directly, okay? Because that this Reynolds number is not the same, right? You cannot compare this directly because this Reynolds number is not the same. And because that in the laminar cases, you usually have a small Reynolds number, okay? Local Reynolds number, and in the turbulent field, you have a larger Reynolds number, okay? Although that in these cases, this maybe looks, if you have the same value Reynolds number for both cases, okay, this may be larger than it. But the problem is that in the laminar field, okay, at this point and at this point here, these two Reynolds number is not same. Okay? So usually this is much smaller than the Reynolds number here. So that's the reason that even you calculate this one, this will be still larger than this one. Okay. So let me correct this. Okay. Actually, the turbulence will try to increase the viscous force, and that's why the boundary layer thickness become increasing. My fault. All right, so I know that it is a little bit confusing because problem me, okay, but I just want to emphasize that the effect turbulence will be actually, enhance the wall friction. That's why that the boundary layer will increasing, because that the friction, the wall friction effect will extend to a larger distance. Okay, although this coefficient looks this is bigger than this one, but you cannot just compare the coefficient directly, because that this Reynolds number on the laminar cases will be much smaller than this Reynolds number than in the turbulent cases. Right. Mm-hmm. Okay, so if you draw the tau of W as a function of Reynolds number, okay, so what it looks like? It will looks like this. So if you have this critical number, if you look at first laminar with something like this drop, okay, to this one, and then increasing and drop again. Okay, this will be what the turbulent, what this tau W looks like. This number. Okay. This is something we just cannot compare the direction. Okay, any question, guys? No. The important thing is this final result. Okay, is that in the laminar cases and in the turbulent cases, how the coefficient and is changed. How this power of -1/2 is changed to this power of -1/5 instead. Okay, and these things. Okay, how this delta x is increasing in the turbulence. All right, so this is hydraulic performance of the turbulence boundary layer. So what is the thermal performance? What's the heat transfer rate? Okay, the heat transfer rate is like we can still solve those energy equations, right? All those boundary layer equations. But there is a simpler way people usually doing. Okay, they're doing analogy solution. Okay, they're just thinking that the mechanism of the heat transfer is similar to the mechanism of momentum transfer. Basically means that we consider that there's a analogy between, between the we have this tau W equal to mu du dy, right? And we have this q prime prime W will equal to minus k dt dy at y equal to 0, at y equal to 0. Okay, so this is a transport correlation, right? For u, and this is a transport correlation for the t. Both of them are transport equation. So we consider there is an analogy between tau W and this q prime prime W. Okay, and also similarly, we will have an analogy between this CFX and to this Knudsen number. Okay, so we want to find this analogy correlations here. Okay, so basically means that let's rewrite the shear stress, right? For the shear stress, we have this equal to rho mu plus mu t partial u partial y. Shear stress we have the contribution from the mean term and from the turbulent term. This is ideal viscosity. This is the mean bulk viscosity. And the similar thing for the total heat transfer rate, we have this q prime prime. We can include equal to rho cp alpha plus alpha t partial y. Okay, and this alpha is the mean bulk thermal diffusivity, and this alpha t is the thermal ID diffusivity, alpha t. Okay, and so we can rewrite this equation, tau equal to this one, q prime equal to this one. Okay, just rewrite it. Divided this term on the both to the left, divided this term to the left. So you will rewrite this term to this partial u partial y equal to tau rho mu plus mu t, and partial t partial y equal to q prime prime over rho cp alpha plus alpha t. Okay, so this is what we can get, and then we integrate the above equations from the location at the wall, okay, to some point in the free stream at a distance L, okay, from the wall. Just basically that you have a wall here, okay. Just integrate from some places to a big Y, okay, to this distance here, from this region to here for these two equations, and assume that this L is large enough, is outside of the boundary, boundary layer, okay. That's the reason that when you do this integration, okay, first when you integrate this one equation, du dy, right? We know that at the wall, this u velocity will come to 0, and at this larger region L is in the free stream, so this u mean velocity will become u infinity. So that's the reason that you only left the u infinity here. And then on the right hand side, it's 0 to L, tau over rho mu plus mu t, right? Just do integration on this one. And similar things that you do integration on this one. And at the wall, you have wall temperature, and at the location L, you have free stream temperature T infinity. So when you do that integration, you get T wall minus T infinity. I have a minus sign. I added a minus sign is that to try to make sure that the Q prime direction is on this positive direction. Okay. So basically, there should be a minus sign here, but I just neglected it for simplification. But this will be TW minus T infinity will be equal to TW minus T infinity. Okay, from the wall minus infinity upper stream. So that's the direction will be this one, Q prime. And will be integration of this one. Okay. So this is just simple integration. And so the first analogy is called let's see, what they call it? The Reynolds analogy or Prentice analogy? This is called the Prentice analogy. So basically means that we want to have the correlation between these two, right? So we want to analog the heat transfer in turbulence with the momentum transfer. So the way to do this is that we assume this two Prandtl number equal to 1. Okay, the bulk Prandtl number equal to 1 means that we assume that the kinetic viscosity equal to the thermal diffusivity, the bulk. And also we assume that in the turbulent field, okay, this turbulent Prandtl number is also equal to 1. So that we have this mu t equal to alpha t. Okay. So when we have these two here, you can rewrite this equation TW minus T infinity. Okay, replace this alpha plus alpha t to this mu plus mu t, right? So this is just rewrite this equation here. Okay. And also that because it has the same, because it's an analogy, okay, we also assume that the distribution of the total shear, so this tau, okay, and this Q prime prime along this y direction, right? Because we do this integration, right? This tau and this Q prime on this y direction. They also has the same profile, okay? The profile is similar. So assume that the distributions of total shear stress and heat transfer rate are similar. That at any point in the boundary, so we can have that this Q prime prime divided by Q prime at the wall will be equal to tau over tau at the wall at any location on this inside this boundary layer. Okay, in the boundary layer. Okay, I mean there's one word here. And so what does this mean? This means that we have this correlation here. Then you can rewrite this Q prime prime with this equal to tau divided by tau w times Q prime QW prime, right? So you just basically you rewrite this equation, you replace this equation with these three terms. So you have this tau w minus T infinity equal to QW prime prime divided by T tau wall, and you still have this integration term here. Okay. And if this is constant, okay, you can move this out. Sorry, this not this system. So if this CP is constant, you move this out. Okay. And then this integral L from 0 to L tau over rho mu plus mu t will be just equal to U infinity. Okay. You just bring this into this integral here. Okay. So you rewrite it, regroup it. Okay, you basically will have the TW minus T infinity divided by U infinity will be equal to the QW prime prime divided by CP times tau w. So by here, okay, we finally create correlations between the, heat transfer and shear stress for the momentum transfer, right? Okay, tau w or u infinity and q wall. Okay, so this is shear stress, and this is the heat transfer rate. Okay, and with this, then we can calculate what the q prime prime, because this tau w we already know from our previous solution here, right? We know from the velocity distribution, we already able to calculate this tau w for the hydraulic performance for the in the turbulent parameter. So with this question, with this correlation, you can directly calculate what the QW prime will be. So we simply regroup this a little bit to make the parameter non-dimensionalized, and the final result basically this will be final result. It's showing that the local Nussel number at x location, okay, will be equal to the the friction factor, local friction factor divided by 2, okay, and times the Reynolds number and times the local Reynolds number, and then times Prandtl number. And because we assume this Prandtl number equal to 1, okay, in this Prandtl's analogy, so you can just remove this Reynolds number. So this will be the final result. The Nussel number will be just equal to CFX divided by 2 times Reynolds x. So this is the simple way that how we can find what the heat transfer in the turbulent boundary layer. Simple way. And if you bring the previous result we have here, bring this half by if we're using this Prandtl's 1/7 power law, okay, you bring this correlation for the CFX, you can immediately get the what the Nussel number will be, okay, and just that you just have this 0.0296 here, you have this 0.0296 here, and you have this because this is the Reynolds number minus 1/5, and you times another Reynolds number, so you will have Reynolds number 4/5, which is the Reynolds number 0.8. So this will be the Nussel number for the in the turbulence boundary layer, okay, and then you can do a mean, okay, just do an integration, on x between 0 and x. So this will be results for the mean Nussel number. So this is a simple analogy, which is called so-called Prandtl's analogy. But this, you see that this analogy has some limitations because that we assume the Prandtl number equal to 1 for both bulk Prandtl number and the turbulent Prandtl number. Okay, so basically it means that we neglect any difference in the fluids. Okay, because that we know that for different fluids, the guy for the air Prandtl number is equal approximately to 0.7, right? For the water, Prandtl number is close to 7 or something. So for different fluids, actually the Prandtl number will change, will be different a lot. And we know that Prandtl number is fluid properties. So that means that this analogy doesn't consider the differences between different types of fluids. So there's a better analogy, which is so-called Coburn's analogy. So this is also the one used in our textbook. From there, based on is an empirical analogy. Okay, basically means that this is not derived from any theory, it's just derived from the experimental data. What does it mean? It means that they have this correlation. This ST is so-called the Stanton's number. Okay, Stanton number times Prandtl number to the power 2/3 will be equal to 1/2 CFX. Okay, and this Stanton number is defined as the Nussel number divided by Reynolds number, and also divided by a Prandtl number. Okay, so this is the Stanton number correlation. So if you're using this Coburn's analogy, because that is including the effects of Prandtl number, right? Because it's divided Prandtl number here and then times the Prandtl number or 2 or 3. If you're still using this Prandtl's 1/7 law for this CF value, you're still using this we derived from this Prandtl's 1/7 law. this will be your final result. So Nussel number X will be equal to this one. Okay, and there is a range for this Coben analogy can be used. Okay, this Coben analogy is only working for this prandtl number for this range. Okay, so that's the reason that we have this larger than 0.5. So you bring that Prandtl's 1/7th law CF(x) value. You bring it here, so you get this value. You get this value here. So for both local Nussel number and mean Nussel number, you compare these two with the result we have here. You see that the only difference is that you have the additional term here, right? You compare these two equations and these two. You see that the only difference between this Prandtl's analogy and this Coben's analogy is that we have an additional term for the effects of the Prandtl number. So that's why this is better, because it considers the difference of the different fluids, different types of fluids, the Prandtl number difference. Okay, so this will be the final result. Looks like okay, in the what will the flat plate? Okay, what's the heat transfer in the turbulent boundary layer? Okay, again we can still just try to have to recall what we have before. Okay, for the laminar cases. Okay, what will be right? For the laminar cases, if we're using Blasius, yeah, so Nussel number of X will be equal to 0.322, right? Reynolds number X 1/2, Prandtl number 1/3. For Prandtl number is larger than 0.5, and also you have for this 0.564. Reynolds number X 1/5, and Prandtl number 1/5. Prandtl number is smaller than 0.5. Okay, and so you can compare with this when this Prandtl number is larger than 0.5. You can compare this correlation with this one. Okay, for the laminar cases, you also have this 0 to x of average is just equal to ux. Okay, you have this average. So you compare this one, the turbulence and the laminar results. You can see that how the heat transfer is changed, right? You're seeing that okay, so effect Prandtl number is to the power of 1 or 3, so they are same, but the difference showing in the Reynolds number. This Reynolds number is to the power of 4 or 5, and this to the Reynolds number is the power of 1 or 2, and also the coefficient is not same. Okay. So this is what the view looks like. Okay, because you cannot just compare the coefficient again. Okay, because that the Reynolds number, this value in the turbulence is much larger than this Reynolds number in the laminar. Okay, so you need to compare case by case. I forgot that picture looks like. So if we draw a Nussel number, okay, you can try to draw this yourself on this Reynolds number, okay, and then you have this Reynolds number CR. Okay, so what is the view looks like? So it will be something like this, and then immediately jump like this, something like this, the Nussel number, something like this. I believe so. Okay, I will confirm it in the next class for this, something like this. Jump. We can plot this ourselves. Okay, if we assume this equal to 5 times 10 to 5. Okay, just draw this plot. Okay. So this is this will finish our discussion of the how the turbulence affects the boundary layer problem, right, for the flow over flat plate. And what's the conclusion we have here? The conclusion is just that now we have the new correlations. Okay, you have these new correlations. So let me. Sorry. So we have these new correlations. Okay. Let me make it cleaner. We have this new correlation to calculate the nuisance number. This one here. Okay. And we also have the new correlations to calculate the this CF value. And also we have new correlations to calculate the boundary layer thickness for the turbulence. So this is the important thing. Okay, you need to know that in the turbulence field, how to calculate the boundary layer thickness, how to calculate the friction, and how to calculate the nuisance number. And also you know that how we get this equation, right? From the velocity field, we just purely for this friction, we just purely get this result based on this velocity profile, and which we assume, which is in most cases we assume that this 1/7 power law, which this is solution derived from this profile here. Okay, and on the temperature, on the thermal one, this result is we're using a so-called Coburn's analogy, so that we have an analogy between the heat transfer in turbulence field and also the momentum transfer in the turbulence field. The analogy between the tau W and QW prime prime. Okay, analogy between these two, so that simpler we get this equation. Yeah, so this is the result. And if you read your textbook, okay, and you know later on when you do your own research, you will find that this result we got from this Coburn analogy is not very accurate. Okay, and many researchers, okay, in these days they still try to publish papers, try to find a new correlations, this nuisance number equal in the turbulence field, how this is related to Reynolds number and Prandtl number. Okay, and they, you can find the new correlations in the papers. Okay, most of them is from their experimental work. So a lot of empirical correlations you can find. Okay, just be careful that as I talked in the last class. Okay, anytime when you're using empirical correlations, okay, this is like analytical, right? Because this is from this law. It's not fully analytical because this is also some assumption. You can think of this semi-analytical and analytical solution. But for this one is a pure empirical, okay, correlation. So analytical results, okay, they also have a range to apply, right? Like maybe this is only working for turbulent field, they only working for laminar field. But usually speaking, that analytical results, okay, even you using it for the flow condition a little bit outside of their applicable range, flow condition range, the results definitely will have error, right? But that error will not be too big. But empirical correlations will be different. Empirical correlations, you need to be very careful that for their applicable range. Okay, so if you're using some empirical correlations with some flow conditions or flow fluids not suitable for this empirical correlation, it may bring you a very big error. Okay, so that's the reason that for empirical correlation, you just be very careful that in which range it can be used. All right. So any question?
No.
All right. Okay. So let me see how many times we left. Okay. So we will go to the next chapter. So this is the turbulence effects on the external flow. So the next one is the turbulence effect on the internal flow, right? And so here we only discuss the the flow inside the pipes, okay? And for different Reynolds number, which is calculated based on the hydraulic diameter, okay? Times dH divided mu, okay? Divided mu, okay? This is the mean velocity, okay? And dH is the hydraulic diameter of the pipe, okay? Based on the different value of this Reynolds number, you are fully developed flow, Okay, all these three cases is the fully developed flow. Okay, maybe have the maybe in the different flow regime. Okay, it can be either in laminar or in transitional or turbulence. Okay, laminar basically you can think that if you track a flow particle, okay, their streamline is like mostly like a keep unchanged. Okay, or you know, and for the transitional regime, you can consider that you know you see some little turbulence effect, so the streamline okay become you know some you know curved or wavy the behavior. But if the Reynolds number is become very large, okay, this Reynolds number become very large. If you track the flow will become full turbulent. Okay, you will have if you track the streamline will cross to each other, and you know you will have those you know vortices here, vortices here, vortices here. Okay, have a lot of vortices increasing. So this is the flow will become turbulent flow. Okay, so to distinguish between the laminar, transitional, turbulent flows is we using this is usually you know critical Reynolds number value will be okay. The critical Reynolds number usually considered as the 3300. Okay, and is defined by um times dh over mu. Um is the mean velocity. dh is hydraulic hydraulic diameter. Hydraulic diameter is 4 times AC, and AC is the cross-sectional area divided by the P wide. Okay, is the wide parameter. And for the circular pipe, it just the diameter for this DH. Okay. So this is how you distinguish that you know if the fully developed flow in the flow inside pipes are the laminar turbulence or you know laminar or turbulence. So yeah, just consider that if Reynolds number is smaller than 2300 is they are laminar. When the turbulence is larger than 2300, it will become turbulent. Okay. Another special thing for the internal flow is that we have that concept of developing flow and fully developed flow, right? For developing flow, we need to know that the length, right, the entry length, that in which cases the flow will become fully developed, how long the flow will become different. Right? So just remember that for laminar cases, right? You know, so this is from our chapter 3 lecture. We know that the entry length, okay, this big X for the diameter for the you know for the velocity boundary layer, okay, will be equal approximated to 0.005 Reynolds number, right? And for X over T, this is the entry length for the thermal boundary layer, okay, divided by T equal to 0.05 Reynolds number times D times PR, right? So this is what we have before for the laminar cases. But for the turbulent field is that what people observe is that you know the turbulence flow internal flows will become fully developed very quickly. Okay, just after like a 10 diameter length. Okay, just you know after a very short distance from the entrance, the flow will just become fully developed. So this is from engineering standing point. Okay, what the empirical correlation that people using. Okay, basically saying that if this length, okay, if this is entrance somewhere here, okay, this length to here is already larger than 10 times the diameter size of this circular pipe. You know, we consider that the flow is already become fully developed for the turbulent flows. All right. Then we looking at so this is for the developing flow. Let's looking about the profiles of the fully developed flow. Okay. For fully developed flow, if you look in the velocity field for laminar, okay. So this is the laminar velocity profile, and it will have the maximum velocity at the center line. Okay. This is where the velocity has the maximum value. And we know that this maximum velocity, the center line velocity is like to be twice of the mean velocity. Okay, this is from our analytical result we got before, right? So center line velocity will be twice of the mean velocity for the laminar cases. But for the turbulent cases, it's not like that. The turbulent cases is that it will quickly, okay, starting from the wall, is quickly approaching to a large value rather than this short value, straight large slope here, okay. And around the center line, okay, the center line velocity will not that as big as the velocity the center line velocity you have in the laminar cases. So center line velocity, the mean velocity just like not like a 1/2. This is the mean velocity in this case. This line is mean, okay. This line is mean, okay. So mean velocity in this case is 0.5 of the center line. This one is only 0.8 or approximately 0.8 of the center line. We will try to show you this later, okay, from our velocity profile in the turbulent field. And for the temperature field is same thing, okay. For the fully developed temperature field, let me remind for the laminar, just remind what the laminar will be. We have this U of R divided by U of C equal to 1 minus R over R squared, right? So this is our result. The velocity profile will be. And for the temperature profile is TW minus T divided by TW minus TC, okay? If this temperature is constant, right? We have this 1 minus 403 R over R squared plus 103 R over R4. Okay? So this is the laminar, in the laminar cases, what the velocity distribution for fully developed flow, and what the temperature distribution for fully developed flow, right? So if you draw this one in this field, TW minus T divided by TW minus T of C, the profile will something looks like this. But for the turbulent one, it's also changing. Okay, the temperature field it's not like you have a long, transition region from here to the maximum value. It will quickly, approaching to a large value, and then, going down. Okay. So this is the temperature field, how the profile is changes. Temperature profile changes in the turbulent field compared to the laminar field. Okay. And usually speaking is that when flow becomes the turbulence, because of become turbulence means that you increase Reynolds number. All right, you increase, for example, you increase this mean velocity. You can increase in this mean velocity by increasing this Reynolds number. Basically, usually speaking, that the larger the velocity increasing, you'll have a higher pressure drop. Likely, okay, means that this friction factor F will likely to increase, and also that you have higher velocity, turbulent velocity increasing, you would like to have a larger heat transfer rate, right? And basically means that your Nusselt number will also increasing, something like that. Okay. Okay. So this is just some descriptive analysis, like how the affects turbulence for the flow inside the pipes. And then we also need to know that what the governing equation will be. Okay. And this is laminar governing equation, right? But as we talking about before, that the laminar governing equation is still the same equation for the instantaneous quantities, because they are follow the same conservation laws, continuity, momentum, and energy, right? So basically, this is, let me emphasize it again, okay? Working for instantaneous quantities, okay? All right, because they are still, you can still derive this equation from the same conservation laws, okay? And so this will be, okay? And but some terms is missing, okay? Like for the x momentum, there should be also velocity, viscous effects, okay, on this on the x direction. So this term should be also has a mu times this term here. but this term is neglected because that for this problem they consider that the U is changing on R direction more than U changing on the X direction. Okay, you know that what I want to say is that you also should have a mu of partial square U partial X square. Okay, you should have this term, but this term is neglected. Okay, for this equation. And also for the temperature, similar thing. Okay, you also should have a alpha partial square T of partial X square. But you know, because that you do scaling analysis, the temperature changing on the R direction is much larger than temperature changing on the X direction. So this is also neglected. And also again on the Y, we only have X momentum. We neglect Y momentum. We still assume that on the Y momentum, the V velocity, you know, the pressure basically just telling you that the pressure is only a function of X, not a function of R. Okay. And again, for okay, when you do Reynolds averaging on these three equations, you will have additional. Okay, you will have this additional. What I say, additional Reynolds stress terms, U prime, V prime on here, similar to what we have in our external turbulent boundary layer cases. Okay, you will have this also Reynolds stress for the temperature fluctuation term. So and again, you define the ideal viscosity and thermal ideal diffusivity, mu T alpha T here. Okay, and you do the averaging on the three term. Yeah, so this will be the final. This will be the final solution will be for the Reynolds averaged governing equations. So you have the momentum, and you have the X momentum, this continuity equation of X momentum and energy equation. Okay. All right, and so this is what looks like for pipe flow. Okay, so this will be the R direction, and this will be the X direction. Okay, R is on this direction, and this one we consider the X direction. If it's fully, if we consider fully developed cases, okay. For fully developed cases, is like if the flow is fully developed, you can consider that this du dx will go to 0. The u velocity is only function of r, and also v velocity becomes 0. Okay, because there's no velocity on the r direction, so this will go to 0. So basically means that all convective term is gone. Okay, for fully developed. So for this equation, you can simply just writing that the pressure drop is equal to the viscous term. Okay, or you can write this equal to this, and you do an integral on r. First, you can calculate this. You can correlating the pressure drop and with this partial per u partial r value. And similar things for the fully developed cases, right? V equal to 0, so this will gone. But this one is not 0, okay? Because T is still changing, okay? Temperature is still changing because that even for fully developed flow, depending on your boundary condition, if is T wall is constant or your QW prime wall is constant, okay? This one will still a function of X. Temperature is still changing, okay? What I mean is that this T is still changing, okay? But it's only this TW minus T between TW, both T and TC is changing even for fully developed flow, but their ratio is not changing. Okay, so in this case, only this term is to 0. So you can write the, you can further simplify the energy equation just to equal to this one equal to this. Okay. So this is the energy equation. Sorry, this is the conservation equation. We can try to solve. If we can solve this numerically, we will obtain that the full, resolution of the velocity and temperature field. So we can know that from the velocity we can know that what the pressure drop will be, and from the temperature result we can know that what the heat transfer will be. Okay, but in this class we won't go details for the numerical method. We still try to derive in the problem, the solution, in some analytical way. Okay. So first we still looking the hydraulic performance. Okay. similar to that before. We want to see that what the velocity distribution will be in the turbulence field. And from the velocity distribution in the turbulence field, we try to find that what the pressure, the friction factor and the pressure drop will be for the turbulent, fully developed turbulent pipe flow. Okay. So first thing is that just recall that what the friction factor will be. Remember that in the we like to use this CFX for external flow, right? I think we remember I mentioned this before. And for the internal flow, we like using smaller f. Okay. So that is some convention, like from the previous people doing research, they prefer to do this. So for the internal flow, we will have this volume factor, friction factor defined as F equal to tau W divided by 1/2 rho U mean square. Okay, and so to want to solve this friction factor, right? Want to solve this tau W, we need to know the velocity profile, and we want to know that what the turbulence velocity profile will be. Again, okay, we can still define that the U plus is equal to some function of Y plus, and based on different region, we can have this inner region where it's very close to the wall. We can consider it's just laminar and no turbulence. And in the buffer region, we can see that the turbulence has some effects here, but it's not dominant. And then outer region, when Y plus is become very big, it's fully turbulence. We need to find this the FU distribution will be. Okay. And similar thing, okay, considered as a center line. Okay. And this Y plus, okay, this Y direction, remember that this Y value is the value, from the wall, starting from the wall. Okay. So basically means that this Y will basically equal to R minus R. Okay. So if you have any point in the middle here, okay, so this distance will be R, but this value will become to Y. The Y value is the distance to the wall, okay, and the R value is the distance to the center line. Okay, so that's the reason that Y equal to R minus R. You need to know that this difference here, and consider as a point at the center line. Okay, at the center line, the U will become to UC, okay, and then U plus will become UC divided by tau W divided by rho to the square root. So this is the friction velocity U star. And for Y plus, okay, and at the center line, Y will be equal to R, okay. At the center line, the Y value will be this length, which is Y equal to R, and times this U star divided by mu, okay. So that means that let me write it, at a point on center line, okay. We will have this correlation, okay. And for this one, look at this correlation here, okay. We want to know if so how many unknowns in this case we have, okay. We do not know the tau W in these cases, okay. And I think that's it. And the UC, although we do not know it, okay. Although we do not know the UC, but the UC can be directly calculated based on the FU, based on this velocity profile. So we can, from the velocity profile, can know the UC already. For this one, you only have one unknown tau W. Okay. So what that means is that if you know this velocity, profile in this turbulent field, from this single equation, okay, this single thing is sufficient for you to find the tau W. Okay. So what the simplest this FU profile will be? We're still using this Prandtl 1/7 power law, okay, because this is working for all the cases, and when there is a wall, okay. Just consider that this is a wall. This is a wall here, okay, and this will be the profile will be, okay, U over UC. This is the solution, okay. Solution from this profile, U over UC will be Y divided by R to the power 1/7. Or if you change this y to this, r minus r, it will become 1 minus r over r 1/7. You have this profile here. Okay, let's try to use this simplest profile. You using this profile, you try to calculate the mean velocity. Okay, mean velocity. will be 1 over pi r squared. So this is the cross-sectional area of the pipe, this circular pipe. And from, you do 0 to r for r and theta from 0 to 2 pi for this u to, just do this, bring this correlation into here. You can find the correlations between UC and UM. You find that this is equal to 120 over 98, okay? And this is approximate, this is this approximation we got here, okay? That's why we see that, U mean is like approximate 0.8 of UC. You can get it from here, because UM is like 98 over 120, this value, okay? So we got the correlations like, what's the center line comparing to the mean velocity. And then we can calculate the friction factor, right? So friction factor is then calculated by, you just simply bring this, changing this UC to UM, okay, to UM here. So you get the whole U profile. After you get U profile, okay, you do the mu times partial U partial R at, okay, R equal to 0, R equal to R, you get the wall, you get tau W, okay. After you get tau W, you divide it by 1 over rho UM square, okay. From this velocity profile, you can, based on this friction factor here, you can calculate that what the friction factor will be. The friction factor in this case, it will be 0.078 Reynolds number to the minus power 1 over 4. Okay, so basically means that you have this velocity profile, you know what the mean will, UC to U mean will be. You bring this, you replace this UC with U mean, and you calculate the U, gradient at the wall, get the tau W and divided by 1 over UM squared. You will get this friction factor. Okay, and so this is one result. Okay, the result we got, the friction factor will be based on this Prandtlen's 1/7 law. It's the same thing. Okay, this is not very so physically this law is not accurate, but mathematically it's very simple. That's the reason we use it. But physically it's not very accurate. And if you're using a better correlation for FU, you're using this correlation here, so this law and rule here, you can get another, friction factor correlations, okay, with this real number. But for these cases, it's a little bit complicated because this is a implicit function for F, which means that for any Reynolds number, you need to find the root of this F value to find the F, okay, for this correlation. So you may need to want to do using some iteration way to find what the F will be. Okay, and you also have some empirical correlations. One empirical correlation is from the Blasius. Don't misconfusing. Don't be confused this one with the laminar cases, okay? Because it's from Blasius, but this Blasius, this researcher is he does many researches, okay? This is for the turbulence, okay? It's not the Blasius solution for our laminar boundary layer turbulent pipe flow, okay? Not a laminar boundary layer solution for Blasius, okay? He's the same guy, but he also developed his based on his experimental data for what F will be. You can see that this is experimental data, empirical relation, and this one is very close from this 1/7 law, very close. But this is not commonly using. This is what we commonly using from the empirical data. This is an empirical correlation for what F will be in the fully developed turbulent pipe flow but only for high Reynolds number. This empirical correlation is only in the range for this large Reynolds number when Reynolds number is larger than 20,000. Okay, remember that we consider our transitional Reynolds number 2300. So this is value is much larger than that RECR. Okay, critical Reynolds number. So that's why it means this is only working for high Reynolds number. It's empirical, and this is some very commonly used F value, friction value you can use for fully developed turbulent pipe flow. Okay, all right. And after you got F friction factor, either from this one or either from this one or from this one, you can calculate pressure drop. Okay, and remember that this friction factor, this F is the Fanning. Okay, Fanning friction factor. Okay, not the Darcy. Okay, I remember it, and this is the Darcy. I just want to emphasize it again because that in some textbook you will see that the reason you may read in some textbooks the F value they write it here basically is 4 times this value, 4 times this value, 4 times this value here, 4 times the value. That's because is that they are using Darcy, not using the Fanning. Okay, for Darcy this is equal to 4 5. Okay, and for the Fanning cases, so if you're using the Fanning friction factor, the delta P is calculated in this correlation shape, F times 4 times divided by DH times 1/2 rho U mean square. Okay, or if you want to change in this rho UM to the G. Okay, G is a so-called so mass flux. Okay, it's basically M dot over rho. Yes, yeah, this is M dot over rho. Okay, so this is called a mass flux. Okay, you can find this definitely in your previous notes actually. So if you want to use Darcy, okay, if you for some types they using Darcy, when they calculate pressure loss, they will combine this 4 and this F together just to F of D. Okay, so that you won't see of this 4 correlation here. So what I want to say that if you read some textbook or some paper, when they calculate the pressure drop, you won't see this 4. That means that the F they're using here is Darcy, not the Fanning. Okay? So that's the things I want to show you. And if this dPdx is a constant through the pipe, so the overall pressure drop for the whole pipe can be just calculated dPdx times this length of the pipe. So this is how the fully developed turbulent flow, what the friction factor will be, right? And again, okay, just want to remind you what the laminar case what we have. For laminar, F just equal to 16 over Reynolds number. Okay, so you can compare this one with either this one or this one. And if you draw a friction factor corresponding to Reynolds number, right? You can draw it yourself based on this correlation Reynolds number and based on our critical Reynolds number. So if we have this RECR here, so because this is 16 over RE, right? It will be a straight line going down here, and then you jumping, and then a curve going a curve, sorry, a curve going down, something like that. Okay. So this is the friction factor will looks like. They have a sudden jump on the critical point here. So this is how the turbulence effects of the friction. Okay, so any question, guys?
Yeah. What are we supposed to know from all that?
What are you supposed to know for what?
Like from what we just did, what are we supposed to, like, what did we just solve?
I think that you can either using this one, because this is showing in a lot of academic textbook, because it's very from that Prentice 1/7 law, right? So it's very standard. A lot of people using, but it's only people using it to work for the academic textbook problems. But in the real practical problem, okay, like you want to solve a real do an experimental data, you want to do experiments, you estimate that, what's the pressure drop for pipes flowing a pipes if it's turbulent. This is more accurate. But be careful is that this is only working for a large Reynolds number starting from 20,000. Okay, so it's like if its Reynolds number is smaller than this value, this cannot use. You have to find another one. You may either using this one or using the you can try to find any literature, textbook or whatever. You can try to find, because there are many literature or textbooks. They will give you a table that with different this F value for turbulence. Many references from many people. Put it there. You can choose one you think is accurate. Regarding to the homework or exam, you can either use this one or this one if the range is satisfied. I think both are okay to me actually. Okay, because this is more like an analytical result and this is more like an empirical result. Okay. More questions? Okay, that's good. So this is how the turbulence in the pipe flow changes the friction. And then the next question is that how the turbulence changes the heat transfer in the pipe flow. It's similar thing than before. Okay, we want to solve the problem numerically. All right. So because that requires you to solve the full Rance equation with some turbulence model. We don't want to do that. We're still using the so-called analogy method. Okay, analogy solution for fully developed pipe flow. We same thing. Okay, we're starting from the Reynolds analogy. We define this tau Q prime prime. With the contents the both bulk term and turbulence term. Okay, the bulk viscosity, ID viscosity, the bulk thermal diffusivity, and the thermal ID diffusivity here. Okay, and we just follow the similar procedure we have before for the turbulent boundary layer problem. Okay. Just be realized that the difference between Y and R, okay, basically it means that, I just write it here again, okay, R basically means R minus Y, okay, or something. So this is Y is the distance starting from to the wall, but R is the start distance from the center line, okay. You have this equation, this result here for tau and this result here for the Q prime prime. You regroup it again to tau. Only left this partial U, partial Y, and partial T, partial Y on the left-hand side. Again, you do integration. Here, you integration from 0, okay, which Y to 0 at the wall, to any points to Y value, okay, in this pipe flow, okay. So to integrate from Y to 0 to Y, any point Y. Y can be anything between 0 and R, okay. So for U infinity, it's for, at this point, you will have U mean and T mean, okay, at this value, at Y value. And at the wall, U velocity will become 0. So that's the reason when you do this integration from 0 to Y, you only left is the U mean, okay. At this point, you have U mean equal to from 0 to Y tau divided by rho mu plus mu T. And similar things for your integration this on Y for the temperature. At the wall, you have T equal to T wall, okay. And at this Y location, you have T equal to T mean. So basically T wall minus T mean equal to 0 to Y, Q prime prime rho CP Ty. And this is same thing what we did before. And we still assume that, Prandtl's analogy, right? We assume that the Prandtl number and for both bulk and turbulence equal to 1, which means that the turbulence mu T equal to alpha T, bulk mu equal to alpha. We also will assume that this Q prime prime and tau, they have the same profile, which means that at any point inside this pipe flow, there's Q prime prime over Q prime prime W will be equal to tau over tau prime prime W for the point has a Y location. Okay. You bring this one into this T equation here. Replace the Q prime prime with this. Replace the Q prime with these 3 terms here. We will get this one, T infinity minus T mean will be Q prime prime divided by tau W equal from 0 to Y, tau divided by these things. Okay. And let's define. Okay, define this integral. It's just a function of y. Okay, assume that it's just a function of y because it's integrated from 0 to y. So their end result will be something related to y. Okay, so you can rewrite that because u is this one, right? This we define it as a g of y. So basically, u will just equal to g of y equal to this one, and tw minus t will be qw prime prime divided by tw, and move this cp out. Okay, you only have a row here, so it will become g times y. Okay, so this g of y is an unknown function. Okay, because that our null number and the Reynolds number is defined on the mean velocity, right? So we need to calculate what the mean velocity will be. So you need to calculate both the mean velocity and the mean temperature, because that this mean velocity is used for the Reynolds number, and this mean temperature is used for the we define for the Nussbaum number, because Nussbaum number we are using this TW minus TM to define the Nussbaum number. Where is it? Okay, I will show you later. Okay, so you need to find what the average Reynolds velocity number. So this is how we calculate it, right? Basically, your integral on velocity on the heat on the r direction and divided by a cross-sectional area. And so for the mean temperature velocity, basically means that you calculate this ut. You can consider this as if times Cp, this is like an enthalpy. Okay, if Cp is constant, like you integrate the enthalpy on the r direction and divided by the mean enthalpy value if you type Cp here. Okay. So this is UMTM. And remember that this y equal to r minus r. So you replace this r to y, dr to the dy. So what you get that this will be um value 2 over r squared, because this pi is cancelled, here. And u of r minus y, okay, because u is a function of r of y here. And similar things, you have this t of mean value. And because you bring this also to this here, so you have the additional term on the bottom. So it will become u a function of r minus y times t a function of r minus y times dy, and u times a function of r minus y times dy. So this parenthesis here, this parenthesis here is not like this t times this value. No, it just means that this is u and t. U is now is a function of r minus y, not the function of r anymore. Okay, so times dy. Okay. You have these things, these two, and you then bring this because you have this u bar here, right? You replace the u bar equal to this g value. So for this one, it will become g r minus 1. Okay, that's you replace this u bar with this g value. You have this g square. Similar for the tm here, u become to g. Okay, and temperature, because this temperature field is also related to this g things. Just basically we bring these two equations for u and t to the equation ut here. You get the result of this two new additional term, um and tw minus tm, which is a function of g here, a function of g here to the integration. Okay, we do not know what the g will be. Okay, and if you're using this equation divided by the first equation, you get the relationship between the temperature and velocity field. Tw minus tm divided by qw prime prime times Cp tau w will become to these things. Okay, and the whole this whole term, because it's is integrated from for the y value. Okay, from 0 to r. Okay, and the result will be a function of f. We just to make this notation a little bit shorter, just denote this whole term as f. This is definition of f here. Okay, and so this is the an analogy result. Okay, basically it's telling us that the qw prime prime and tau w, can be related to this Cp temperature difference and the mean velocity. So if we regroup it together, you will get Nussbaum number, and and the Reynolds number in some way, okay, because tau W for the Reynolds number, you get a relationship between the friction and the heat transfer rate. The only thing is that you do not know this F term. The one simple way is still using that 1/7 Prandt's Prandt's 1/7 law, okay? 1/7 law. So is that you assume U divided by UC equal to Y over R 1/7. So this will become G because this is definition of the G. So this is definition of G, sorry. U equal to Gy, right? So you know that this will be G. And you bring this G value into this equation, you can calculate the F. So basically, you will know that F will be, this result will be 150 over 147 in these cases. It's very close to 1. So in most cases, we just consider it's 1. And if you bring F equal to 1 here, you're just telling us that this tau W minus tau M divided by UM equal to QW prime prime divided by CP over times tau W. Okay, so this is a Reynolds analogy telling us that you know what's the heat flux and you know relationship between the heat flux and friction force. But in our cases, right, we won't using the tau W. We would like to relate it to the friction factor F. Okay, so we need to convert this tau W to the small finding friction factor F. To do that, you just simply do a you know momentum conservation on a control volume inside the pipe flow. Okay, you have this pressure force, you have this viscous force. Okay, so pressure force times this area, cross-sectional area, minus pressure force on the other side times cross-sectional area will be equal to the tau W, so the drag force times this parameter times this distance, which is this wall surface area. Okay. So from this momentum balance, you will calculate, you will know that dP over times over dx equal to minus tau W times 4 over d. And know that tau W will, because this is dP dx, right? Remember that just replace the dP dx with this correlations pressure drop we gave before here. dP dx equal to 4, dP equal to F times 4 divided by d times 1 over 2 rho u square, rho u m square. Bring this dP dx to this correlation here, you can get the correlations between tau W and F. Basically, tau W will be F over 2 times rho u m square. All right. So by this correlation, you can replace this tau W to the friction factor. So just replace this one to here. So you get that tau W minus you get the TW minus TM divided by UM will be equal to this heat flux, wall heat flux divided by Cp times 2 over F rho UM square. Okay, so this is the result. And just regroup it together to make it the parameter all become the non-dimensional parameters. Okay, on the left hand side, you just simply move this QW prime and you just divide the temperature difference to the right, and QW prime divided by this temperature difference is the H. Okay, so this is H, film coefficient, and times the distance, times diameter D with the pipe divided by K, fluid thermal conductivity. This will be Nusselt number. HD over K is Nusselt number. And on the right hand side, you can regroup it. This will be the Reynolds number, and this will be Prandtl number. Okay. So what's the result? The result basically telling us that okay, in this analogy, we know that in the turbulent field, fully developed turbulent pipe flow, the Nusselt number to the based on the diameter D and based on this mean temperature. Okay, definition. Nusselt number will be equal to F over 2 times Reynolds number. This is Reynolds number, F over 2 here, times the Prandtl number. And because this analogy, right, we assume that the Prandtl number equal to 1. So this Prandtl number here will be equal to 1. And the final result will be Nusselt number equal to F over 2 times Reynolds number. Okay, and if we're using this, you know, if we're using this result, okay, friction factor result from this, also from this 1/7 law, F equal to 0.078 Reynolds number to the power minus 1/4. Okay, and we can just calculate that in this case, the Nussbaum number will be just equal to 0.039 Reynolds number to the power 3/4. So this is the way that you can using this simple Prandtl's analogy. You can calculate the Nussbaum number will be. Okay, using analogy, you know, find what the thermal performance will be. So this is the mean value. And again, okay, similar things. This Reynolds analogy, they didn't consider any fluid difference. Okay, because they all consider we consider the Prandtl number equal to 1. So that means that, but we know that for different fluids, we have different Prandtl number. So the textbook give a more accurate result analogy. Okay, they call the Coben analogy. You know, similar to Coben analogy we use for the external flow. It's also empirical correlation. Basically, it's telling us that standard number times Prandtl number 2 or 3 will approximate to F over 2, and this is what the standard number will be. And so you just regroup it. Okay, this will be final result. Nussbaum number equal to F over 2 times Reynolds number times Prandtl number to 1/3. So compare with this one. Okay, this result compare with this one, we only add an additional term, Prandtl number to the power 1/3, to, you know, to account for the additional effects of the Prandtl number. Again, okay, so if you're using this as a result, so this will be the solution. Okay, and if you're using that this empirical correlation for F, you will get this result. If you use this one, you will get this result. Okay, so this is the more commonly used in the engineering analysis. Nussbaum number is 0.023. You will see this 0.023 very frequently for the turbulent pipe flow. All right, and there are more commonly used empirical correlations for the fully developed turbulent pipe flow. Okay, one is the most commonly used is the Ditto spoilers. Okay, this is very commonly used. People use it everywhere. Okay, so Nussbaum number basically is 0.023 Reynolds number d/28 Reynolds number to power 0.8 Prandtl number to unknown power n, and you know, this guy developed this in 1913 actually. Basically, he want to use this n equal to 0.3 when it's cooling. Okay, basically means that flow is you know, the liquid, the flow, the pipe flow is losing the temperature. Okay, it transfers the heat to the wall. Or n equal to 0.4 for the heating. This is from his. This is also empirical. Okay, it's empirical correlation. Okay, you can see that this 0.3 and 0.4 basically. Okay, you see that this 0.023. We also have this 0.023, so they are not coincident. They are not. This value is not like you know, we got this arbitrary. Okay, it's like a different researcher. You know, they all coming to this same constant. And this one got this Prandtl number 1/3, and we know that 1/3 is 0.3333, right? But for this guy, this correlation, he just like n either 0.3 or 0.4. So 0.3333, 1/3 does something between these two. Okay, and this correlation is used for when Prandtl number in this range and the Reynolds number is very large. Okay, and also we have like other correlation, like you know, Janicki's correlation. Nussbaum number is a very complicated correlation with the friction factor, and you know, after you know the friction factor, you can calculate the Nussbaum number. And in the textbook, they also list many other empirical correlations for the turbulent Nussbaum number. Okay, for the Nussbaum number for the pipe flow. But remember, okay, all the cases I'm showing here is only for the T-VOG to constant case. Okay, the result I showing here is T wall to constant. Okay, T wall to constant. And if it's a Q wall, okay, constant heat flux boundary condition for the pipe flow, you need to go to the literature to find other correlations. Okay, the literature do have those correlations for Nussbaum number, but for the things you see here is only for the constant wall temperature conditions. Do not use these correlations for the constant wall heat flux cases. Okay, if you use that in that case, the result will be very wrong. All right. Any question here, guys? Okay, so oh, I forgot one more thing. So I forgot to compare with the laminar cases. So what the laminar will be? Just remember what we have before. For laminar cases flow, Nussbaum number will be 11 over 48. I remember. So, oh, sorry, not 11, 48 over 11 is a constant for the fully developed laminar flow. When Tw equal to constant, okay, which is close to 4.363, right? So if you draw a Nussbaum number, a Reynolds critical value, okay, so it's like a constant at some value here, okay, and then after it reaches to this critical value, it will become something. I think there's this. I forgot it's going down or going. It should be something like this actually. We can bring this Reynolds number equal to 2300 to here to see what it will be. Will that be smaller or larger than this value? It also depends on different Prandtl number definitely. Usually something like this actually. Okay. So this will be the effects of turbulence for the internal flows actually. So same thing, okay. When we're talking about all these turbulence effects for external and internal flow, just focusing on that, what the critical Reynolds number will be, basically telling you that when each flow is a laminar or turbulence, and what the profile will change, like this, like for the laminar boundary layer, right? Profile is more full than this one, and the velocity profile in the internal flow, like you will not like centerline velocity will not as high as the laminar cases. You need to know this, and also that you definitely will know that those CFX or at small f value, frequent vector value, how they are changing, and how the Nussbaum number is changed when you have this turbulence field. This is the things will be. Okay. So then we finish the turbulence analysis for internal flow. The last one for the turbulent effect for the natural convection, right? We talk about the turbulence effect for the internal flow and external flow, and similar thing for turbulent flow. You also affect for the natural convection. For this free convection, external free convection, like around a vertical place. Okay, along the x direction here, your Rayleigh number will increasing, right? In the beginning, it will be laminar, but when the Rayleigh number is increasing to a very large value, it will become turbulent, and this will be the critical Rayleigh number will be. Okay, and how this turbulence changing turbulence affects the Nussbaum number, okay, heat transfer rate. Actually, when we're talking about this in our previous chapter, okay, let me see if I have this. File. Okay. Is this one? This is internal. So it should be this one. No, this one. So, let me open. Let me open it. I just want to bring our previous notes actually. So chapter 4, 2. I think is this one. Okay. Like you remember that when we're talking about this, how the friction is, how the how we what the Nusselt number will be, right? This is one example. Let me see. Do I have another example? Vertical plate. Vertical plate. Huh. Now this one. So let me open another one. Chapter 4. Vertical plate. Okay. Do I have it? Oh, I didn't. I forgot. I forgot where it is. Basically, I want to say is that like some correlations I gave you in the previous lecture note is already included in the correlations for the turbulence actually. This is like this example. Like this is the flow over a cylinder, right? It's like like it looks like this Rayleigh number here. The correlation I gave to you. This in this range, Rayleigh number to the 10 to power 7 or 10 to the power 12 is already including the some turbulence effect already. Okay, but let's go back to our today's lecture notes. But what I want to say is that basically that if you for these laminar cases empirical, if you write these empirical correlations for Nusselt number, will be C times the Rayleigh number to a power n. Okay, for laminar cases like 10 to the power 4, 10 to the power 9, this C can be 0.57 and n can be equal to 1/4. Okay, and let me double check. I think we don't. Mm. 0.59. Okay, so this is not clear. So this is 0.59. Okay, and this is n equal to 1/4. And when turbulence, okay, really the number it become big. Basically, this constant C will become 0.10 and n equal to 1/3. So for the natural convection turbulence effect, we won't go too much. Okay, we will just stop here. So basically, you will know that for these cases, okay, external natural convection, this will be the critical Rayleigh number will be. Okay, and if you want to use these correlations, okay, they will show you that how the turbulence will affect the Nusselt number will be based on because it for different correlations, different coefficients. So this is just some simple things we go through for the turbulence effect for the natural convection. Okay, so here we finish all the, showing that how the turbulence will affect the both forced convection and the free convection. And before we stop today's class, actually, there's an additional topic we want to go through is the for this pipe flow. Okay, we know that what the Nusselt number will be, right? After our analysis, either is laminar or turbulent, no matter what it is. Okay, and if we want to calculate the overall heat transfer rate, how we can do that? Okay, because we know that this Nusselt number, okay, and Let me see. Why it's not changing? Next. Okay. So if is vol is constant, vol is constant, okay, value, and your mean value, okay, is increasing, okay. Mean value is you do not know what the mean value will be, okay. You remember that our Nussel number is defined by h of k over d, right? And the qw prime prime is calculated by h times t vol minus tm, okay? So this is what you know. But for these cases, your vol temperature, your mean temperature actually is keep increasing, okay? Keep increasing even after the flow is fully developed. Your mean temperature of the fluid is keep increasing because it keep receiving the energy from the vol, right? Along the downstream. You know, the vol is keep adding the energy to it until it's finally approaching to vol. You know, if your pipe is infinitely long. Okay, and how we calculate the Q dot? You know, one way you want basically you want to say that okay, we can calculate Q dot like from 0 to L, okay, of x, and QW prime prime of x, okay. But you won't be able to do that because that you know, as you said, this value you do not know it. You do not know what is TMX, what it is, right? So how we can do that? So you can do this using this log mean temperature difference way, okay? First, you can define like the temperature difference as a wall temperature minus mean flow temperature. Okay, so this temperature difference we also changing with x coordinates. At the inlet, we will have this delta T in to equal to TW minus T inlet value. And at the outlet, you will have this wall temperature minus T outlet value, right? And the overall heat transfer rate, you can first calculate based on the temperature difference from the inlet and outlet. So will be equal to m dot Cp times T out minus T in. The problem is that you do not know the outlet temperature because it's affected by this QW prime value, right? Affected how many heat we got from the wall. Okay, but you can rewrite this as m dot Cp equal to delta T in minus delta T out. This one minus this because you simply just cancel this T wall here. You still get this value T out minus T in. Okay, and also again, okay, we can do a energy balance around control volume for the around inside the pipe. Okay, so this is the rho Cp times U times the cross-sectional area. So this will be the mass flow rate times Cp delta T. So this is the, you know, the changes, okay, the changes of flow enthalpy. You know the net changes of the flow enthalpy. And this one is like the overall heat coming in, heat added from the wall, right? Is the parameter P times this control volume dx, the distance, times this wall heat flux. You get the heat added to the fluid, this control volume, and then you rearrange it and write this pair square basically as a like a cross-sectional area, this as a P parameter, and this QW prime as this H times the TW minus TM. You can rewrite them as this DTM minus TW minus TM equal to this HP A times rho Cp UM times dx. Okay. All right. And you integrate on the both side, you know, for this TM value. Okay. And you will get the result like a ln TW minus T in. Okay. Integrate the DTM on the dx from 0 to L. Okay, from the inlet to outlet. So basically, you get the value ln TW minus T in divided by ln divided by TW minus T out will be this HPL A rho Cp UN. Okay, so if you write this as delta T single, you can make it shorter. Ln delta T in divided by ln delta T out with HAW m dot Cp, and this m dot is just this rho times A times UM. Okay, so this is mass flow rate. So this return is m dot. Okay, Cp, and AW is this. This is AW wall. AW is it's a pipe wall surface area, and you have this Q dot here, right? Times and you have this MCP here, right? you also have this m.cp here, right? So basically, you just replace this m.cp with this m.cp here. Basically, you're using this equation to cancel this m.cp. You bring this one and this one to this equation. You will get that q dot will be this value, and this will be its final value. So q dot will be h times aw times delta t Lm, and this delta t Lm is called the so-called log mean temperature difference. Okay, is defined by delta t in minus delta t out times ln delta t in divided by delta t out. Okay, so this is the way you can calculate q dot. But usually, okay, you do not know what the delta t out will be. Okay, the way you can do this is that you from this solution here, maybe you just from this solution here. Okay, you replace, because you have the correlation, right? You replace the delta t out with all the other terms to this equation here, and you will get final result. This one. This is how you calculate the overall heat transfer rate. Q dot equal to m dot cp delta t in times E1 minus times 1 minus exp to the power minus HAW divided by m dot cp. Okay. So this is the overall heat transfer rate for the TW equal to constant. This is just some additional things I want to let you know. And if the wall equal to heat flux constant, that is very simple. Okay. Q dot is just equal to this wall heat flux times the overall heat transfer, overall wall area. And you know, the temperature difference will keep same through the flow. Okay, both the both delta T in will be delta T out will be delta T log M. That's the same thing. Both the M in this case is both the mean temperature and the mean fluid temperature and the wall temperature will keep increasing, but their delta T difference will be same. So because that you want to keep this QW prime equal to constant. That's some additional things. Any question? Yeah, so this is just give you a way that you know how to calculate the overall heat transfer rate for the fully developed flow. Okay, this is working for both laminar and the turbulent cases. Okay. So basically means that if you want to calculate Q dot in these cases, you just need to find the H. Okay, and if you want to find in H, you just need to find the Nusselt number from either turbulence or laminar case, and you get H. You can directly calculate the Q dot. All right, so this is oh, there's one last thing. Okay, I want to let you know for the heat transfer for this problem. I forgot to mention this actually. You remember that for this flow, you know, for this flow over the flat plate, they're always starting with a laminar flow and then turbulent flow later, right? And some equations we have here, like this value here, this is just an integral on this one, right? Remember this? So basically what we did is that maybe we add a new term, new page, okay? So basically what we did is that, you know, for this CF mean, okay, 0 to x, okay, it just equal to L of 1, 0 of L, and 0 x maybe, x of 1. X1, 0 of x of CF x of dx, right? This is what we did, right? To calculate the mean temperature, sorry, mean friction factor from the local friction factor. This is only valid, okay? Only valid when your x is much larger than xCr. Why? Because that for this one, we just using the turbulence one. We didn't using the laminar one. You know talking? When we do this integration, we just directly using, when we do integration here, we just directly using this quantity to here. We didn't using consider any other region. Okay, to get this mean value. But in the realistic cases, okay, if you want to integrate from here to the end, you should separate your integration from the laminar part first, and then the turbulent part. So what is the correct way to do? Okay, the correct way to do this is that if you want to do CF of 0 to x, you really should do is that 1 of xCr, okay, the critical value from the 0 to xCr, okay, and maybe I should not do this. Let me write it. Just 1 over x. Just do an integration of CF of x laminar times dx plus xCr to x CFX turbulent times dx. Okay. So this is that when x is not too larger than okay, is not too larger than xCr. Okay. What I want to say that just some equations you got from the lecture note. Okay, for like this CFX average, like this Nussbaum number average on turbulence quantities, you just assume that this x is much larger than your plate length is much larger than critical location. Okay, so that when you do average, you're just using the turbulence value directly. Okay, but in the realistic cases, if you want to do an average, you want more accurate cases, you need to, because that we know that the laminar cases and turbulent cases, your CFX and Nussbaum number, they are not same. Okay, so you need to integrate it on two parts to do this. So this is another thing I want to mention. So so like similar things like when you calculate this Nussbaum number, right? You have this turbulent Nussbaum number, and when you get this average Nussbaum number, basically you're just integrating on this based on this one. This value you try based on this is not accurate when you if you want to consider the laminar part. If you want to including the laminar part, you need to integrating this part, this value from 0 to that xCr, and that xCr is you calculated based on this critical real number, and then plus, and that's the rest part integrating using this equation, this part, this turbulence number. Okay, so just be careful for this one for your work. All right, so we will finish today's class, and we will have a homework today. Okay, and this will be our last homework. Okay, for next class, we will talking about the two-phase flow, boiling and condensation, how the heat transfer will be. But that one we will not. That part is we won't have homework for that one. Okay. So today I will give you the homework, which will be due next week. The homework problem will be covering all these turbulence effects, and also problem for that internal natural convection, which is for the last class, because we do not have homework for the last class. I didn't upload the homework yet, but I will upload the homework, before 8 o'clock tonight. So do not forget to check the Blackboard for the homework problem. Okay. And so we only have one class left. Let's talk about the next class. Okay, next class I want to go through a little bit for the two-phase flow, boiling and condensation. And then this part usually, okay, is not including in this class in previous, by other lectures. Okay, in previous semester. But because that, after we move to the online teaching, I think we really go through all these lectures very fast, actually. So that we still have one class left. I want to introduce that one because that one is actually important when you do the research, actually, boiling and condensation. You will see a lot of things in the engineering problems, and even in heat exchanger or even in other problems, you always have the boiling condensation, the icing, problems. So I will introduce that part for you in the next class. But as I said, no homework for that part, and that part will not including in the exam. Okay. All right. So, any question?
Are you gonna upload these notes to Blackboard too?
Oh yeah, definitely. Both both these notes and the video, I will upload it to the Blackboard. Your homework 7 is already graded. You should be able to see your score on the Blackboard. I will also upload the homework solution today for that homework 7. And you know, I think that's it. The last thing, okay, final exam is May 18, okay, starting from 5:30. So you have 24 hours for open book. I just want to emphasize this again. All right. So any more questions, guys?
No.
Okay. All right. So I'll see you in next class. Okay. Do not forget to check the Blackboard for today's homework. That's it. Okay. Bye, everyone.
Thank you.
Yeah, you're welcome.